Okay, cool. So we are talking about finite differencing and analytical solutions with Couette and Pascal flow. Finite differencing is a numerical method that's used to approximate derivatives by replacing them with algebraic expressions built from values at nearby points, and it's the area under the curve. So basically, we split into different rectangles and between calculus into algebra. The difference between analytical solutions and numerical solutions. Analytical solutions are exact closed form expressions that satisfy a differential equation for all the points in the domain, and you can only use them for simple geometry and boundary coefficients. Numerical solutions don't have equations, it's just a set of points. You can use them for more complex problems, but there's always amount of error involved with them that analytical solutions don't have as much of. Quick flow is where one plate moves while the other is stationary. It doesn't have a pressure gradient and it has a linear velocity profile. Pascal flow, both of the plates are stationary. It's driven by a pressure gradient and has a parabolic profile, continuous slip at the walls. For both of the problems, you can assume they're Newtonian, constant density and viscosity, no electric field, steady state, no slip. The difference between Couette and Pascal for the pressure, there's no pressure gradient here, and there is a pressure gradient here. But you can also assume for both of them that Vy and Vz equals 0 because it's wide. And we're also assuming for Pascal flow that it's fully developed. And for both of them, you're simplifying the continuity down to dVx divided by dx equals 0. And you can simplify the x momentum balance down for Couette flow down to 0 equals mu d squared Vx divided by dy squared. Integrate twice for both of those, plug in the boundary conditions, and plug those when you solve them for C2 and C1 back into your original velocity. And you can get u divided by h multiplied by y for Couette. Finite differencing, I'll show that in the Excel document for Couette flow. Pascal, same thing for continuity. For the x momentum balance, you do have a pressure gradient, so that ends up simplifying down to delta P divided by L equals d squared Vx divided by dy squared, because you can divide out the viscosities. Once again, integrate twice, apply boundary conditions, and you can get the velocity equation, negative dp divided by 2 mu L multiplied by d squared divided by 4 minus y squared. Same thing for finite differencing. I'll show that in the Excel document. For volumetric flow between the plates in the z direction, you're basically taking the integral from one boundary to the other boundary in regards to the velocity dy. For Couette, it's basically the integral of 0 to h from u h y dy and ends up being 400. Quite finite differencing, you're using rectangles since you don't, a sum of rectangles since you don't have like an actual form to go off of, and that gets you 400, same as the analytical solution. Pascal, same thing, solving for Q, except your boundary conditions are different, and obviously your velocity equation is different, but your boundary conditions plus or minus negative d divided by 2, you can get this number. You get the exact same number for the finite differencing, just doing a sum of rectangles. Same thing that you did for finite differencing. Solve for the shear stress at each plate and the shear force per unit width. For the shear stress, that's basically just mu multiplied by dvx divided by dy, so that's the clock. We're starting that for the boundary conditions, the bottom from the top of the plates, and that's plus or minus mu u divided by h, and f shear is basically just multiplying by the cross-sectional area, which is 300. For quite finite differencing, you're doing the exact same thing with the f shear, but you have to solve for tau with rectangles again, and that gets you, once again, also 300 pascals times centimeters. Pascal analytical, exact same thing that you're doing up there, except you have a different Vx and Y that you're solving for in different boundary conditions. and your analytical and find differencing are slightly different answers, just due to the inherent error that's with finite differencing. And with the Reynolds number, you basically just can simplify the rho u h divided by mu down to rho q h, and you can just plug in what you found earlier into the analytical and find everything for all of these. And once again, a little bit of error with the Pascal, but that's okay. And this is my Excel document. This is the Couette flow. I did the equations. And Pascal. Yay.